Welcome to today's lecture on the RSA algorithm, one of the most widely used cryptographic methods in securing digital communication. In this video, we will explore how RSA works, break it down step by step, and demonstrate it using an example. By the end of this session, you will have a clear understanding of RSA and even see how to implement it in code. The applications of RSA are we are using to secure the mails, banking, and digital signatures. This concept was introduced by Travis, Shamir, and Adliman. It is a public key cryptographic algorithm which is used for secure data transmission. We are using two key concepts here, public key and private key. We will cover in this lecture about the key concepts, understand the step-by-step RSA algorithm, solve an example problem to reinforce theory, see a coding demonstrate of RSA in action. This image illustrates the RSA encryption and decryption process. In the sender side, the message starts as a plain text, which is typically represented in ASCII code. This is the encryption key, which is nothing but the public key. The sender uses the public key E, N to encrypt the plain text message. Public keys are shared openly and used for encryption. In the RSA cipher, the plain text is passed into the RSA encryption algorithm where the public key E, N is applied. The ciphertext is computed as C is equal to M power E mod n, where M is the plain text, E is the public exponent, N is the product of two prime numbers P and Q, and so on. The output of the RSA cipher process is the ciphertext, which sees through the communication channel. The ciphertext travels over the communication channel, which could be in any medium like the internet. The ciphertext is encrypted, so it is secure even if intercepted. On the receiver side, the receiver uses the private key D, N to decrypt the ciphertext. The private key is confidential key and is not shared with anyone. In RSA decipher, the ciphertext is passed into the RSA decryption algorithm, where the private key D, N is applied. The plain text is computed as M is equal to C power D mod N, where C is the ciphertext, D is the private exponent, and N same modulus used during encryption. The output plain text, which is in ASCII code, the decryption process retrieves the original plain text message in its ASCII form, which the receiver can read. And we are using two keys here. Public keys used for encryption is shared, and private key used for decryption is kept secret. This is an asymmetric cryptographic key algorithm. RSA is an asymmetric encryption algorithm, meaning different keys are used for encryption and decryption. The security of RSA relies on the difficulty of factoring large prime numbers, the product of two primes. Let us discuss an example to make this clear. So first, before going to discuss an example, let us discuss about the algorithm. And these are the some of the steps to generate RSA keys. Here we are choosing two different prime numbers, distinct prime numbers P and Q. Then we can compute n is equal to P into Q. Calculate the quotient phi of n is equal to P of 1 into Q minus 1, P minus 1 into Q minus 1. We are choosing one integer e such that 1 less than e less than phi of n. And we have to calculate the GCD of e comma phi of n should be equal to 1. We can compute the d also, the modular multiplicative inverse of e mod phi of n. So this is an example. Let's walk through an example to make this clearer. Suppose we choose two prime numbers. The two prime numbers are p is equal to 61 and p is equal to 53. Then we will compute n is equal to p into q. So p into q is 3233. We will compute the phi of n. Phi of n is equal to p minus 1 into q minus 1. P minus 1 is 61 minus 1 is 60 and 53 minus 1 is 52. So while multiplying these two numbers, we are getting 3120. E choose E value. The E value is 11, which is commonly used, and compute D is equal to 2753. How we are getting D is equal to 2753 means E power, we are taking 17 into 17 into 2753 by mod 3120. So by using this formula, we are getting the value 1. So we are applying the formula here. ED mod phi of n is equal to 1. The plain text we are convert to integer m is equal to 65. Ciphertext we will convert in the form of s is equal to m power e mod n. So the value of m is 65. 60 power e is 17. So 65 power 7 into mod 23232. So we are getting 2790. We will go to the decryption process. The ciphertext is 2790 and the plain text we are taking m is equal to c power d mod n. For example, if we are taking m value, C value 2790, 2790 power 2753 mod 3232. We are getting 65. So this is the decryption process. And the security of RSA will be based on the difficulty of factoring large prime numbers. The security of RSA relies on the difficulty of factoring large prime numbers, the product of two primes, and the key size typically 2048 bits or larger for security. The applications of RSA we will use secure communication, secure socket layer and transport layer security, and digital signatures and data encryption process. These are the sum of applications of RSA. Now, in conclusion, the RSA is a foundational technology in modern cryptography, and here we balance security and performances. Let us walk through the coding part of the RSA algorithm. So this is our program. Now let's see how to implement RSA in code. Here is a Python program that generates keys, encrypts a message and decrypts it. We are using header files here, which enables standard input-output header file stdio.h and which is used for the functions like printf and scanf. And we are using math.h for mathematical functions, not explicitly used here, but included for completeness. This is a function which is used for the greatest common divisor, GCD, which is the purpose of calculates the greatest common divisor, GCD of two numbers using the Euclidean algorithm. Keep replacing A with B and B with A, B with A mod B. When B is equal to 0, A holds the GCD. This is the modular inverse function, which is the purpose of this function is finds the modular inverse D such that ED into phi is not equal to 1. It returns D with the condition is satisfied. This is a brute force approach and can be replaced by the extended Euclidean algorithm for efficiency. Let us calculate the modular exponentiation function. This computes base, expression, and mod. Uses this exponentiation by squaring method to reduce the number of multiplications. And it multiplies the current results with the base. And it right shifts expression by text by 1 in each iteration. Squares and base and takes the modulo text in each step. So this is about to calculate modular exponentiation function. Let us go to the main function. Here we are taking two prime numbers. Those are P and Q. So the P we are taking 61 and Q we are taking 53. So these are the two prime numbers which are the foundation for RSA encryption. The product of two primes use it the modulus in encryption and decryption, and phi we are using Euler's torsion function phi of n, the count of integers less than n that are co-prime with n. And E is the public exponent that satisfied GCD of E comma phi equal to 1. It checks if E is valid, otherwise exits the program. In step 4, the private key component D, calculated as the modulo inverse of E modulo phi. We are displaying the public keys here. Public key is equal to E comma N and private key is equal to D comma N. In step 5, we will encrypt the message. This takes the plain text message M and calculates the ciphertext C. C is equal to M power E mod N. And coming to decrypt the message, it takes the ciphertext C and calculates the original message. The formula here we are using M is equal to C power D mod N. So this is all about the coding part of this RSA algorithm. The input is the plain text. The ciphertext after encryption is nothing but the encrypted message. The plain text message retrieved after decryption is the decrypted message. Okay, so this program demonstrates the RSA algorithm step by step, generate public key and private keys, encrypt a message using the public key, and decrypt the message by using the private key. Let us run this program. So this is the output we are getting after running this program. The public key, here we are taking E comma N, E value 17 and N value 3233. And private key we are taking B is equal to 2753 and N is equal to 3233. Original message we are taking 65 after applying the encrypted message. That means ciphertext. That means C is equal to M power E mod N. We are getting 2790. Decrypted message. Decrypted message means we are converting, finding out the plain text. M is equal to C power D mod N. So ciphertext power decryption key mod N. So we are getting 65. If you observe clearly here, original message and decrypted messages both are same. This means whatever we have done is correct. So this is all about RSA algorithm. Thank you. Thank you one and all.